In this video, we'll take a look at why non-terminating repeating decimal numbers are rational. Now, we won't be doing a formal proof of this result here. That is, we won't be showing that all non-terminating repeating decimals are indeed rational numbers. Instead, we'll take a few examples of this type of number and show that they can be written as fractions where both the numerator and the denominator are integers. That is, we'll show that they're rational numbers. And then hopefully you'll be able to take those ideas and extend them to all non-terminating repeating decimal numbers. So let's begin with a fairly simple case. We'll start with the number 4.22222 and so on. So you can see that this is definitely a non-terminating decimal, and you can also see the repetition here. We have 2 followed by 2 followed by 2 and so on. So how do we write this as a ratio of integers? That is, how do we write it as a fraction where the numerator and denominator are both integers? Well, to start, I'm going to do something that might seem a little bit strange. I'm going to give it a name. I'm going to call this number x. So we'll write x equals 4.22222 and so on. And then I'm going to do something else that might seem a little bit weird. I'm going to multiply it by 10. Now, if I do that, and I'll write it up here and you'll see why momentarily, think about what happens when we multiply by 10. Ultimately, we get the decimal moving one place to the right. So we'd have 42.22222 and so on. And those 2's continue forever. Now this is not x anymore because we multiplied by 10. So we could call that 10x. For the next step, I'm going to do some subtractions. I'll start with what's on the left side here. 10x minus x. Well, if I have 10 x's and I take away 1x, I have 9 x's. So I'll write 9x. On the right side, I have 42.2222 repeated minus 4.22222 and so on. Well, 42 minus 4 is 38. And because we have a string of repeated 2's here minus a string of repeated 2's here, we'll get 0 when we subtract those decimals. So the answer is simply 38. Now we can write that these two results are equal. And think about why. We know that 10x was equal to this, and we know that x is equal to this. So therefore, if we do this minus this, we should get the exact same result as if we do this minus this. So that is indeed true, and I'll just write a little note here that we subtracted. Now at this point you might be wondering, where are we going with this? And what was the point of those subtractions? Why did we do that? Well, you're about to see. Just hang in there for one more minute. Notice that we have a small equation here that we can solve for x. 9x equals 38. So how do we solve for x? Well, we need to get rid of this multiplication by 9. And the inverse operation of multiplication is division. So we'll divide both sides of our equation by 9, and that will get rid of the multiplication by 9 on the left. So we have x equals 38 ninths. And we're done. Think about what we have here. X is 38 ninths. But a minute ago, we had x is 4.22222 and so on. So we can conclude that this decimal number, 4.22222 repeated, is the same as 38 ninths. So we can say, therefore, 4.22222 repeated is 38 ninths. Therefore, this number is a rational number since it can be written as an integer over an integer. Let's try a couple more examples that are slightly different. How about 5.212121 and so on? Again, I'll call that number x, so x equals 5.212121 repeated. But this time, I'm not going to multiply by 10. Looking back at the first example, the reason I multiplied by 10 was because the decimal repeated every digit. In our new example, the decimal repeats every 2 digits. So this time I'm going to multiply by a number that moves the decimal over 2 digits, and that number is 100. So I'll write out 100x equals 521.212121 and so on. Again, we'll subtract, and this time what do we get? Well, 100x take away 1x would give us 99x. 521 minus 5 is 516. And again, all those numbers after the decimal subtract off to give us 0. So we get simply 516 on the right side of our equation. Solving for x again, we'll divide both sides by 99 this time. And that gives us x equals 516 over 99, which we can actually reduce because both of these numbers are divisible by 3. So if we divide them by 3, we get x equals 172 over 33. And there it is, an expression for this number as a fraction using only integers. So we can say, therefore, 5.212121 repeated is actually just 172 over 33. Therefore, this decimal number is indeed a rational number. And let's just do one more for fun. We'll go with 8.764764 repeated. We'll call that number x. So x equals 8.764764, so on. And this time we want to multiply by a number that moves the decimal place 3 digits because the pattern after the decimal repeats every 3 digits. So we'll multiply by 1,000. So 1,000x equals, and when we multiply by 1,000, we'll have 8,764. So 8,764.764764 repeated. And let's subtract. So we'll write subtract here again. What does that give us? Well, that'll give us 999x on the left side, and 8,764 minus 8 gives us 8,756. And all those decimals subtract off. So x, if we divide by 999 on both sides, we get x equals 8,756 over 999. And there it is, another expression for this number x here, but this time written as a fraction using only integers. So we can see that that decimal we started with is indeed a rational number. So therefore, 8.764764 repeated is actually 8,756 over 999. So hopefully you can see at this point that as long as we start with a repeating non-terminating decimal number, we can always write it as a ratio of integers. It's just a question of what we need to multiply by in this step here. And of course, that number all comes down to how many digits make up the repeating pattern. And just before we end this video, I'll leave you with something that you can try. A very popular question that I'm often asked by students. And that question is, does 0.99999 repeated equal 1? And I'm not going to tell you the answer, but if you take the ideas from this video and apply it here, I think you'll be able to come up with an answer for yourself. So have fun with that.